Hello everyone, welcome to this session on Network Function Virtualization, or NFV, in 5G networks. NFV is transforming the way we manage network functions by replacing traditional, dedicated hardware with software-based solutions. In this session, we will explore what NFV is, how it integrates with 5G, its core components, benefits, challenges, and real-world applications. Whether you're an IT professional, a telecom engineer, or simply curious about how modern networks function, this presentation will give you a clear understanding of why NFV is crucial for the evolution of 5G. Let us begin by understanding what NFV is and why it is needed. So, what exactly is NFV? NFV, or Network Function Virtualization, is a revolutionary approach in telecommunications where network functions like routing, firewalls, and load balancing are implemented as software rather than being tied to dedicated hardware appliances. This means that instead of purchasing and deploying expensive physical devices for each network function, service providers can now run these functions as virtualized applications on standard servers, making the entire system more agile and cost-effective. Think of it like moving from traditional landline phones to cloud-based communication apps like Zoom or Microsoft Teams. Instead of relying on fixed hardware, the functions are now flexible and software-driven. To understand why NFV is so important, let us compare it with traditional network architecture. In traditional networks, each function such as a router, firewall, or load balancer requires a dedicated hardware device. These physical appliances are costly, difficult to scale, and often lead to vendor lock-in, meaning that organizations are limited to specific hardware providers. With NFV, these functions are virtualized and can run on standard hardware, eliminating the dependency on specialized devices. This approach allows for dynamic scaling, automation, and interoperability among different vendors. Think of the difference between using a physical DVD player versus streaming movies online. With streaming, you don't need multiple devices for different formats. It's all handled through software, just like NFV virtualizes network functions. NFV is made up of three main components that work together to deliver network functions virtually. Virtual network functions, VNFs, these are software implementations of network functions like routers, firewalls, and load balancers. Instead of being dedicated hardware, these functions now run as software. NFV infrastructure, NFVI, this is the physical and virtual computing, storage, and network resources required to host and support VNFs. Essentially, this is where all the virtualized network functions run. NFV management and orchestration, MANO, this component is responsible for automating the deployment, management, and scaling of VNFs. It ensures that virtualized functions are working efficiently and optimally. A good analogy is a cloud data center. VNFs are the applications, NFVI is the physical infrastructure, and MANO is the system that automates everything, ensuring smooth operations. Now, why is NFV so beneficial for 5G networks? There are three major advantages. Flexibility. NFV allows service providers to deploy network functions wherever needed. Functions can be moved and adjusted dynamically based on demand, ensuring optimal resource usage. Cost reduction. By eliminating the need for expensive, dedicated hardware, NFV significantly lowers both capital and operational expenses. Service providers can consolidate multiple functions on shared hardware. Faster innovation. New services that previously took months to deploy can now be launched in a matter of minutes. This agility enables telecom companies to introduce and test new technologies with minimal risk. For example, if a telecom provider suddenly needs to scale up firewall protection due to a cyber attack, NFV allows them to do so instantly without waiting for new hardware installation. NFV and 5G complement each other perfectly because NFV provides the programmable and virtualized infrastructure that 5G networks require. From a technical perspective, NFV makes it easier to manage 5G's complex, software-driven network operations. It allows for dynamic adaptation of network resources, which is crucial for handling the diverse use cases of 5G such as high-speed data services, IoT connectivity, and ultra-reliable low-latency applications. From a business standpoint, NFV reduces operational costs and increases service agility, helping telecom providers deliver faster, more efficient services. Ultimately, NFV shifts the focus from expensive hardware investments to software-defined, automated, and scalable network operations, which is exactly what 5G needs to thrive. Network slicing is one of 5G's most powerful features, allowing multiple virtual networks to operate on a shared physical infrastructure. NFV plays a crucial role in enabling network slicing by dynamically creating and managing these slices based on specific requirements. Slice creation NFV allows service providers to define and deploy network slices tailored for different applications, such as IoT devices, high-speed streaming, or critical communications. Slice management components orchestrate and manage these slices, ensuring proper allocation of resources. Dynamic adaptation NFV allows network slices to scale automatically, adapting to changing demands in real time. For example, in a smart city, NFV could help create one network slice for low-power IoT sensors and another slice for high-speed emergency communications, ensuring both work efficiently without interfering with each other. NFV extends its benefits beyond the core network by integrating with edge computing, a critical aspect of 5G. Edge computing allows processing to happen closer to the user, reducing the latency associated with sending data back and forth to central servers. NFV enables network functions to be deployed at the edge, meaning applications that require real-time response such as autonomous vehicles, AR/VR experiences, and remote surgeries can function with minimal delay. Think of edge computing as setting up small Wi-Fi routers in different rooms of a large house. Instead of all devices relying on a single router far away, local routers provide faster connections right where they are needed. With NFV, edge-based virtual functions improve response times, reduce congestion, and optimize bandwidth usage. While NFV offers many advantages, it also comes with challenges that organizations must address. Performance optimization: virtualized functions must match the performance of dedicated hardware, which can be a challenge. Integration complexity: existing legacy network systems must be integrated with NFV solutions, which can be complicated. Security concerns: virtualized environments introduce new vulnerabilities that require strong security measures. Skills gap: many IT professionals are trained in traditional hardware-based networking and need to upskill for software-driven networking. To successfully implement NFV, organizations need proper planning, security strategies, and investment in workforce training. NFV isn't just a concept, it is built on global standards and industry efforts to ensure smooth adoption. The most important standard comes from the European Telecommunications Standards Institute, or ETSI, which developed the foundational NFV reference architecture. This framework defines the key components, interfaces, and best practices for NFV deployment. Apart from ETSI, several open-source projects like ONAP, Open Network Automation Platform, OSM, Open Source Mano, and OpenF, Open Platform for NFV, help in accelerating NFV adoption by providing open and collaborative implementations. Telecom providers also form industry alliances to test NFV interoperability, ensuring that different NFV solutions can work together seamlessly. This is key to preventing vendor lock-in and promoting innovation in the industry. For NFV to work efficiently, it needs proper orchestration. NFV orchestration is the process of automating the deployment, scaling, and lifecycle management of virtualized network functions. There are 4 key steps in NFV orchestration: Service design. This is where network services are defined using templates. It outlines which VNFs will be used and how they will interact. Resource allocation. The NFV orchestrator identifies available hardware resources and assigns them based on service requirements. Deployment. VNFs are instantiated, configured, and connected to form a complete network service. Lifecycle management. Once deployed, the system continuously monitors and manages VNFs, adjusting resources dynamically as needed. Think of NFV orchestration as cloud service management, where resources are provisioned, monitored, and adjusted automatically without manual intervention. NFV is not just about cost savings, it fundamentally transforms how networks operate. It brings automation. Manual network configuration tasks are replaced with automated, software-driven processes. Remote software updates. Instead of replacing physical hardware, updates can be done remotely through software patches. Dynamic scaling. Resources are automatically adjusted based on network demand, ensuring optimal performance. Continuous integration. Instead of major network upgrades every few years, NFV enables smaller, more frequent updates for better stability. This shift means that network engineers need to develop software and cloud skills while still maintaining traditional networking knowledge. NFV works even better when combined with software-defined networking, SDN. Here's how they complement each other. NFV focuses on virtualizing network functions, making them software-based. SDN separates network control from hardware, making network management programmable. When combined, NFV and SDN create fully software-driven, automated, and agile networks. For example, a telecom provider can use SDN to dynamically route traffic, while NFV ensures that firewalls, load balancers, and other functions are running efficiently. This combination is what enables 5G networks to be ultra-flexible and adaptive to real-world demands. NFV isn't just a theory, it's already powering many real-world 5G applications. Enhanced mobile broadband, IMB, virtualized content delivery networks, CDNs, help deliver high-definition video streaming and support traffic spikes dynamically. Massive Machine-Type Communications, MMTC, NFV enables lightweight virtual IoT gateways that can handle millions of connected devices, critical for smart cities and industrial IoT. Ultra-reliable low-latency communications, ULC, NFV ensures real-time network functions run at the edge, reducing latency for mission-critical applications like remote surgeries and autonomous vehicles. These use cases demonstrate how NFV enables agile, scalable, and cost-efficient 5G services. With NFV, security becomes more complex because virtualized environments introduce new attack surfaces. Here's how NFV helps secure 5G networks. Isolation. Virtual network functions, VNFs, operate in separate virtual environments, preventing attacks from spreading. Encryption. Secure communication protocols ensure that data moving between VNFs remains protected. Authentication. NFV enforces strict identity verification, allowing only authorized components to interact. Monitoring. AI-driven security monitoring continuously scans for threats, responding in real time. Since NFV environments are highly dynamic, automated security controls are crucial for protecting virtualized network functions in 5G. One challenge in NFV adoption is ensuring that virtualized functions match traditional hardware performance. Here's how performance can be optimized. Hardware acceleration technologies like DPDK and SIOV improve network packet processing, making VNFs as fast as hardware-based appliances. Resource allocation algorithms. AI-driven scheduling ensures that resources are distributed efficiently across different network functions. Containerized VNFs. Instead of running in heavy virtual machines, lighter containers reduce overhead and start up faster. These optimizations allow NFV to deliver high-speed, reliable, and scalable network functions without compromising on performance. The next evolution of NFV is Cloud-Native Network Functions, CNFs. Instead of using virtual machines, CNFs run in containers, making them more efficient, scalable, and lightweight. For example, traditional VNFs are like large software suites that take time to install, while CNFs are like modular microservices that can be deployed instantly. This cloud-native approach will be key in making 5G faster, more automated, and AI-driven. Several telecom providers have successfully deployed NFV. For example, AT&T virtualized 75% of its network functions, leading to faster service deployment and lower costs. Similarly, Vodafone integrated NFV into its 5G core, improving network slicing efficiency. These real-world implementations show that NFV isn't just a concept, it's a proven technology that is already making networks more scalable, agile, and cost-effective. In summary, NFV is revolutionizing 5G networks by making them more agile, scalable, and cost-efficient. As NFV continues to evolve, we will see even more automation, AI-driven optimization, and cloud-native architectures, paving the way for 6G and beyond. The future of networking is software-driven, virtualized, and intelligent, and NFV is at the heart of this transformation. Thank you for your time. If you have any questions, I'd be happy to answer them.